The action potential is one of the most important physiological concepts on the MCAT. It's also one of the most challenging to understand. I'm Tyler Farah, and in this lesson, we're going to take a close look at the action potential. You'll learn a lot of the nuance and the mathematics of the action potential in medical school itself. For right now, it's sufficient to know how the potential across the membrane changes throughout the action potential, the names of those different states and the ions that are responsible for them, and that should give you enough foundation to handle anything that the MCAT throws at you, whether it's a drug or a toxin or some kind of a physiological imbalance that leads to disruption of the action potential. Knowing these things, you'll have all the knowledge that you need to explore this topic deeper in medical school. Take a moment and read through this question stem right now. This question stem is so characteristic of the MCAT. It may not be in the ABCD format of the MCAT, but the kind of thought that you're going to have to give this question is exactly the kind of thought the test makers are expecting of you on test day. In particular, this question does not ask, do you know the different parts of the action potential? Instead, it asks about how some physiological state might disrupt or change the action potential. And what the test makers are getting at is that if you want to answer this question, you not only have to know the parts of the action potential, but you have to be able to think critically about how changing circumstances might change what you know in real time. So with that in mind, we're going to attack this question by first learning about the action potential, and then we're going to talk about how hyperkalemia might affect the action potential. Let's begin. To understand the action potential, we first have to understand what the neuron looks like when it's just sitting there at rest. And to understand the resting potential, we start with the sodium-potassium ATPase. So this first question is a little bit of a trivia question, but it's important that you know it, so I'm going to ask, what does the sodium-potassium ATPase do? Pictured in the top right is a diagram of a cell membrane with the inside of the cell represented at the top and the outside at the bottom. And the sodium-potassium ATPase takes those two ions and pumps sodium out and potassium in an antiport mechanism. 3 sodium for every 2 potassium for every ATP that gets spent. The net effect of this is to set up these large concentration gradients of these two different positively charged ions. And this is the first step in generating a resting electric membrane potential across the cell's membrane. However, I want to zoom in on that word potential for a moment. That technically means electric potential, but that electric potential comes from the potential of these ions to flow back down their concentration gradients, bringing positive charge either into or out of the cell. With just the ATPase, there's no actual potential for flow across the membrane, and so technically the resting potential so far should be 0. This is where the sodium and potassium leak channels come into play. These allow sodium ions to leak into the cell and potassium ions to leak out of the cell, and that leakiness lends electric potential. Let's start with the potassium leak channels. These allow the slow leak of positive charge out of the cell. And I want you to think, what effect should that have on the electric potential across this membrane? This slow leak of positive charge out of the cell is going to drive its potential in the negative direction. So importantly, potassium efflux out of the cell is going to make the cell's membrane potential more negative. Same drill for sodium. What effect would you expect that this slow gain of positive charge is going to have on the cell's membrane potential? It should make a lot of sense that in this case, we have another positive ion doing the opposite thing, this time coming into the cell, and that slow gain of positive charge drives the potential in the upward direction towards the positive end of the spectrum. Again, remember, sodium influx is going to cause the potential to become more positive. The last thing to recognize about the resting membrane potential is that it sits squarely on the negative side of the spectrum. So to check all these concepts so far, we have sodium leaking in and potassium leaking out. Which of these effects is dominating and therefore driving the overall resting membrane potential? The answer is that while both sodium and potassium play a role in establishing the membrane potential, Potassium's role is much more influential. There must be many more of these potassium leak channels since the overall resting potential is driven so squarely in the negative direction. But it's important to recognize that there are actually a lot of ions that are playing a role in establishing the resting potential. Sodium and potassium are just two of the major ones. And all of these ions have their own small influence on the overall resting potential. The key word for right now is balance. It may be a little skewed toward potassium, but the resting membrane potential is the product of a balance of leakiness towards ions. In just a moment, we're going to see what happens when that balance gets skewed heavily in favor of one side or the other. This next prompt question asks us for the role that the potassium cation plays in the action potential itself. However, if you remember from your outside studies or maybe from your undergraduate education, it's actually the sodium ion that's going to act first. But before anything happens, we need some kind of a triggering event that's going to start out the action potential. My question for you is, what is that triggering event? What's going to actually cause the action potential to fire? To trigger an action potential, what has to happen is that the membrane must become slightly more positive and reach the threshold potential. Now, this can happen for any number of reasons, and one of the most common reasons is that neurotransmitters might land on our nerve cell, opening a couple of neurotransmitter-triggered channels, which let a little positive charge in. In fact, this is actually how cell-to-cell communication among nerves happens. There are other reasons why we might hit the threshold. In fact, if you've ever had a random muscle twitch, you know that sometimes nerve cells just hit their threshold randomly and fire action potentials. But my next question for you is, having hit this threshold for whatever reason, what happens next? Reaching the threshold potential triggers many voltage-gated sodium channels to open. This is a separate channel type from the leak channel. And in fact, for each individual sodium leak channel, there are going to be actually thousands of these voltage-gated sodium channels that open. So if our membrane was slightly permeable to sodium influx with the leak channels, now it's like the floodgates have been opened. And again, sodium's influence is to drive the potential toward the positive direction. So with these many voltage-gated sodium channels open, we would expect to see the potential skyrocket toward the positive direction, peaking out around plus 35 millivolts. My next question for you is, what is this state called? The name of this state is a depolarization or a depolarized state. Where this term comes from is the idea that our cell was heading towards zero overall potential. And that's where scientists got the term depolarized from. It just so happens that our cell overshot the mark and continued actually toward a positive potential. While we're on the subject of depolarization, I want to take a moment and address one of the most common misperceptions about the action potential, which is that when these voltage-gated sodium channels open, many students imagine that there must be this huge flood of sodium cations into the membrane, and that's what drives the potential in the positive direction. That's actually not the case. In fact, during depolarization, very few ions, relatively speaking, actually move. Depolarization is just too short for there to be an appreciable change in the concentration gradients of sodium. To illustrate what's actually happening, I want you to imagine that you and like 10,000 other people are outside of a concert venue, kind of bunched up around the entrance. And suddenly, those doors to the venue fly open, and there's this huge surge of people trying to get into the venue. But then just a few moments later, those doors slam shut. Sure, a few people are going to make it into the venue, maybe the people standing at the front of the crowd. But the point is, everyone in that crowd is going to feel that surge of energy the moment that those doors open. This is similar at the membrane during depolarization. The voltage-gated sodium channels open, and there's this surge of sodium ions, and the membrane can feel that surge of energy. But before very many of those sodium ions actually make it through the membrane, those same sodium channels snap shut, and the depolarization phase is over. Having reached this depolarization state, what happens next? Upon reaching its peak depolarization potential, the cell next slams shut its voltage-gated sodium channels and opens up voltage-gated potassium channels. In the same way that there are many thousand voltage-gated sodium channels for every one sodium leak channel, there are also many thousand voltage-gated potassium channels for every one potassium leak channel. And so the exact opposite phenomenon occurs. We see that those potassium channels, upon opening, drive the potential in a very negative direction, in fact, even overshooting our original polarized membrane potential to this new, most negative membrane potential. My next question for you, what is the name of this state? If minus 70 is polarized, well then minus 90 is hyperpolarized. We're at the most negative potential that the cell will ever reach. So the final question on this screen, what happens next? At this point, the voltage-gated potassium channels also slam shut, leaving only the sodium and potassium leak channels still open, and our cell finds itself back in its original position. And notice the time scale. All of this happens on the scale of milliseconds. This is a very, very rapid procedure. That leads us back to our original question. What role does potassium play in the action potential itself? This is important since next we're going to take a look at what effect hyperkalemia has, which is a potassium imbalance. And so it's important to recognize that potassium efflux cancels out the depolarization caused by sodium. All right, now let's take a look at the fun stuff. Let's see how all of these ideas get disrupted by hyperkalemia. Remember from the question stem, hyperkalemia is characterized by a ton of potassium ions in the bloodstream and extracellular spaces. That means that now our neurons are going to be surrounded by this huge quantity of potassium ions. Let's look first at the effect of hyperkalemia on the resting potential, and then we'll take a look at the effect of hyperkalemia on the action potential itself. To start with, we know that the resting potential is established by the slow leak of potassium cations and sodium cations. What effect would you expect hyperkalemia to have on these leak channels? Recall that potassium efflux specifically is what drives the resting membrane potential toward the negative end of the spectrum. And in this case, with tons and tons of potassium outside the cell, it's going to be a lot harder for our potassium cations to flow out of their leak channels and out of the cell. This disrupts that negative potential that is established by potassium leak. And so what we see is that with the disruption of potassium, the overall membrane potential is driven somewhat higher. How would you expect this to affect the cell's activity? From the graph, it appears that our resting potential is now much closer to the threshold potential, and that means that this cell is going to become hyperexcitable. Now, hyperkalemia's effect on the action potential itself. First off, this cell is going to be able to depolarize just fine. Why? The answer is that depolarization is an effect of sodium and those voltage-gated sodium cations, which are not going to be affected by hyperkalemia. However, after depolarization, we'll see a definite effect of hyperkalemia. In fact, in this case, the cell would actually remain depolarized. Again, my question for you, why? Hyperpolarization requires potassium efflux. That rapid shift back to the negative direction is driven by potassium cations and their voltage-gated channels. In fact, taking this a step beyond the MCAT and into medical school itself, patients with hyperkalemia often present with muscle weakness and fatigue. The reason being that their nerves fail to reestablish the resting potential after firing, and their nervous system becomes less responsive. In the broadest strokes possible, the action potential can be described as balance of the effects of sodium and potassium at rest, followed by gross imbalance towards sodium during depolarization, and then gross imbalance toward potassium for hyperpolarization. If you know these three states and the ions that are responsible for them, then you're ready to go answer some MCAT questions and explore some more complex ideas with the action potential. Thanks for tuning in.